So we talked about magnetic media and how it related to floppy disks, and just storage in the late 90s, but it was phased out as optical kind of took off. And by optical we mean compact disks. And compact disc ended up being so cheap to manufacture and had a lot of benefits over just audio tape because you could see the entire surface of the disc, right? Whereas tape, you kind of had to wind it up. So for the same reason that discs were better than tape, compact disc came in and kind of replaced tapes. We did notice that magnetic tape kind of hung around for a long time, even after the disc was there, and that was because of the data density, right? Because you could spool the tapes up, whereas you couldn't with the disc. But the data density for something like a compact disc ended up being much higher, and even a CD had as much or longer recording time, and it had the benefit of not needing to be rewound. So when recordable CDs and just CD manufacturing in general kind of came to the market, it became very cost effective to just literally manufacture trash. So AOL discs were commonly known as a nuisance, and many of us use these as coasters to protect our tables. But we should probably talk a little bit about the way that a compact disc works. So in this case, you've got a laser beam that kind of comes in and it reflects off the back surface. And so there's kind of a groove in there where the laser beam, it comes down focused and it bounces off of the groove. And there are either like high spots where it bounces back or low spots. And we call these lands and pits. And so the difference in depth means that they go a different path length. And that also allows the laser beam to spread out a little bit more. And thus it changes its intensity. So we record, or rather we interpret, brightness as either a 1 or a 0 and darkness as the converse. So you may be surprised to find out that in a silver pressed CD, or rather in all CDs, whether they were recordable or not, this looks a lot like a phonograph record. There's a pre-groove that's already etched into it, just like with a phonograph, and on that groove, that's where you start to burn in the pits and the lands. So in a silver pressed one, we have just like a metal substrate. I think it was aluminum or something like that. And this could just literally be pressed, much like a vinyl record. So in the factories, you could just stamp, and produce tons of these on the assembly line. So that groove is kind of important, right? The size of the laser kind of tells us how wide we have to make the groove, just depending on like how small we can focus the laser beam. So that's the case of something that, by slang was called a silver pressed CD. This came directly out of the factory. But there were other types, and so when we have the recordable CD, obviously you couldn't do that because you don't have the same kind of factory. So instead what they use, they still had the pre-groove, but they would use like a die. And we'll see if we can kind of catch this in the light the right way to where it's kind of visible, if we can see the data layer. Kind of see that ring in there where the ink or the dye has been burned. So in the recordable CD, the laser would come through and just denature that dye and change its color, and that would represent, or at least fool the laser into thinking this is a pit or land in the standard kind of disc. And this is a case where the background was kind of bluish, but there were other types. I mean, there wasn't like a set standard for how to build a CDR. And here we can kind of see the recorded track in it also. So with those, I'd like to do an experiment a little bit later on where we'll shine a laser beam through the CD and see how it bounces off. And that pre-groove, right, where all of these tracks are right next to each other, kind of looks like a diffraction grating. So we can shine the beam on it and then measure the spacing between these things, kind of based on how does the diffraction pattern look on the wall. So that might be interesting. If we were to move on a little bit, so we had recordable CDs and they did what they did, and then they were replaced in time with DVDs. And the DVD is pretty much the same technology. The only real difference is the wavelength of the laser is smaller, which means it's possible to focus it into a much finer point. And therefore our pre-groove, instead of being spaced far apart, we can compact that and get it much closer together. So we should be able to see that in the diffraction pattern. These two DVDs were two different types. One of them is a DVD-R, and I think the other one's a DVD+R. And really, there's not a fundamental difference that the end user would ever see. Okay, this is just something that was a stupid, pointless format war that was instantly defeated as soon as it came out. So, you know, the consumer didn't really see a difference. We can notice that there's a diffraction grading kind of pattern because you guys see the rainbow and the kind of iridescent behavior in the CD. Well, that's clear evidence that there's some kind of diffraction pattern going on in the surface. Beyond DVD, we did have another format war. That was the difference between HD DVD, which I think was mostly supported by Microsoft, and then Blu-ray, which was supported by Sony and their competing, you know, consortiums or whatever they wanted to call themselves at the time. Ultimately, Blu-ray ended up winning that format war, and it was just slightly a little bit better. So the Blu-ray disc uses a wavelength that's even smaller than the DVD. And the underlying technology really is, for the most part, the same. I don't have a Blu-ray player and I don't have any Blu-ray discs. However, I do have an Xbox One game disc. And the underlying technology here, at least in the hardware, it is Blu-ray. And you won't see the label on it because Microsoft isn't too keen to advertise that they're using Sony's Blu-ray technology in its disc format. And it doesn't matter because you're not going to plug this into a Blu-ray player and need compatibility. The important compatibility sign is this one, Xbox One. So that lets you know what hardware will play it. Okay, so we'll look at this under the laser also and see if we can kind of detect the much smaller pre-groove rate. Other optical media that was kind of slated, there were a few kind of vaporware technologies that disappeared. One I was very interested in seeing was called the holographic video disc, or the HVD. It stored its data three-dimensionally. So like DVDs can come in flavors of single layer or double layer, and I think Blu-rays can have like 4 to 8 layers. So it's kind of translucent layers. They'll record in the data disc at some location, and then that's translucent and goes to a more reflective part further down. So the laser can focus at different depths, and it pretty much just stacks more than one disc on top of each other inside the same substrate. The holographic video disc was purely three-dimensional, so it had literal X, Y, and Z coordinates, or I guess theta, phi, and Z coordinates, because they probably use cylindrical coordinates in that system. It pretty much disappeared, but I think a single disc that had the same form factor, so about this big, I don't remember exactly what it was, but it was on the order of terabytes is what it would store. I think the entire Library of Congress would fit on 6 holographic video discs had they ever made it to market. I'm disappointed they didn't, but removable media, as we discovered, pretty much disappeared because flash and solid state drives and external hard drives became dirty cheap and pretty reliable. So there was really no market for it. Just as a refresher, I mentioned the Sony mini disc the last time we talked about this stuff, and it's not exactly the same technology that you would see in a DVD, CD, or Blu-ray. This was called magneto-optical, and the way it worked, it still had a laser that would read and write, but there was a magnetic layer in here instead of the layer of pits and lands. So as the laser interacted with the magnetic substrate, it would be either absorbed or reflected differently based on the magnetic encoding that was in the back. So it was slightly different technology at work. And the writing section, it had to have a magnetic write head in the back. So the laser head would activate it in some way with the write laser, which somehow it didn't quite melt it, but it allowed the magnetic field to be changed on the substrate. And that's when the write head would change the bits to either 1 or 0. And so it was kind of a really clever, unique way of doing it. And this one disc, I think, has the same storage as a standard compact disc. But we can see clearly, you know, they're much different sizes in their form factors. So when we talk about mini discs, they're a little bit different. They're a fascinating technology that uses different principles, but is not part of this discussion. So I think the next thing for us to do is kind of set up our experiment and get ready to take some of those data. So this will be our experiment. I've got the laser beam here. I'll shine it onto the disc, and then it'll cast an image on the wall. Now I can see it right there on the kind of first strut away from the door, but it may not be bright enough for you to see it. So that's too bad. We want to shine it through so when it bounces off the disc here, it'll cast as m equals 0 on the wall, and then as we go up the wall, we'll see m is 1, 2, 3, 4, and so on up on the ceiling. And we'll use some of this information to try to intuit what was the original line spacing in between the disc. So it is really unfortunate that it's so bright outside, and if a few days ago you noticed everything go out, sorry, I kind of need to just turn the sun off for a second, so be patient. Okay, so we turned out the sun, and now I just want to shine my laser beam into the CDR. Okay, so if we were to take a look at my wall, right there, looks like that's the m equals 0 reflection. It just follows the law of reflection here, bouncing off the surface and then back up onto the wall. So the top one, that's m equals 0. And as we look up the ceiling, we can see 1, 2, 3, looks like 4. So the furthest one out looks like m equals 4. And just take notice of the separation spacing here. This is characteristic of the CDR with its diffraction, I don't know, I guess line density, whatever it is. And this could be an interesting calculation for us to find. Let's say for the line spacing where your maximum diffraction angle is 90. Let's say try it at 1, 2, 3. There, say that m equals 4 diffracts at 90 degrees, and see, well, what's the line depth or the line density have to be, and then do it again for the 5 that we can't see and give us a range. You know, check a range and make an estimate, and then compare it to just the standard specs online for what the pre-groove separation spacing is. So now that we've done the CDR, we should go to the DVDR, which we know is more dense. Okay, so now I've got it trained on the DVDR, and we can see on the wall here again is my m equals 0. And as we go up the ceiling, there are not nearly as many. There's number 1, and there looks like number 2. So you can see there are fewer diffraction fringes on the wall, and part of that's because the pre-grooves is denser, right? So with the line spacing being smaller, you get further and further diffraction. Okay, and lastly, I've got an Xbox One game disc. And from this, we can see, here's m equals 0. And I'm trying to find the diffraction next fringe, and there isn't one. There isn't one anywhere on the ceiling. And I'm kind of shifting back and forth to try to find it. It's gone. So apparently, we can't even diffract out to m equals 1 in this case. That's interesting. So if the laser beam has a wavelength of 532 nanometers, use these data and try to estimate a range, you know, like what's the, I guess for the Xbox One, it doesn't help us out much at all, does it? But for the other two, we can do something, try to give some kind of an estimate of the distance between two adjacent grooves in the pre-groove for the CDR and the DVDR. Okay, so that looks like the end of the experiment. We turn the sun back on, and at this point, we just want to kind of play around with those numbers and see, can we experimentally find out what was a range of the pre-groove spacing inside these discs. Okay, so let's think about what we know. Just to kind of reiterate how the CD works, it's got the substrate, and in it, you've got a track. And the track goes around in a giant spiral. And on that spiral, we kind of see it is raised, right? So here are the different tracks. And the laser would come and focus on this track and either burn in pits or lands, right? So 1, 0, 1, 1, 0, et cetera, et cetera, et cetera. And these have to be separated by some distance that we'll call D. So if this is, in a way, a diffraction grating, where we come in with the laser beam, bounce off of it, and then see diffraction on the walls, maybe like this, right? So here's the laser beam. This would be m equals 1, and then we'll have our 2 or 3 or 4 and so on. Our maximum possible diffraction angle we're going to say is 90 degrees. So in our assumption, we took some data and said the largest one of any of these that we saw corresponded to, oh no, where are they at? Okay. So for the CD, we saw M equals 4 was the furthest one out from the central spot. For the DVD, we saw 2. And for the Blu-ray or the Xbox One disc, we didn't see anything. We saw the central spot and that was it. So knowing this, that, well, the true 90-degree diffraction angle would correspond to M equals something. In this case, it's somewhere between 4 and 5, right? Because we could see the 4, we couldn't see the 5. So at 90 degrees, it's 4 with some remainder, right, or some decimal. Okay, so let's use this as an assumption and try to figure out a range. Like if at 90 degrees, the spot that we saw, let's assume it was perfectly at 90 and corresponded to 4, what would the possible D value be? So in the equation, we had D sine theta equals M lambda. We know the wavelength of the green laser was 532, and we knew, let's see, some other things. We said that the sine we're going to set equal to 90 as part of our assumption to figure out the extreme cases, right? The minimum and maximum D. So let's say for the CD, we're trying to solve for D. That, of course, is 1. So D is just equal to M lambda. And that means that D is somewhere between 4 lambdas to 5 lambdas, right? Where M equals 4 or M equals 5. And I already did the math on this with the calculator. And we got 2.1 to 2.6 micrometers distance, right? I mean, that's really 532 times 4, or 532 times 5, and then did the 1,000 conversion. And this I already am a little suspicious about, because when we look this up, the true value, as known just from technical specs on the internet, is 1.6, and that falls outside this range. So something about this doesn't really look right. And I was further disappointed in finding out that the DVD doing the same thing, right? Saying from 1 to 2 would be 1 lambda to 2 lambda. Well, that of course also came out to something that was a little bit nonsensical. Now we're going to predict what M would be in some of these cases. So knowing the real data, where the CD is 1.6 micrometers, the DVD is, looks like 0.74 micrometers, and the Blu-ray is 0.32 micrometers. I'm going to take these D values, plug them into this equation, and now solve instead for M. And in this case, I think the M that I got was 3.007, M was 1.39, and M was 0.6. And in these cases, do these match what we saw? No. Like here, I would drop all the remainders and say I could see all the way up to 3, but I couldn't see 4. I could see up to 1, but I couldn't see 2. And here I couldn't see anything. And based on what we recorded and what we saw, these don't agree, right? So this was a 3 versus a 4. This is a 1 versus a 2. And the 0, I guess, did agree. So something here leaves me very unhappy. And I don't readily have a solution for what had happened. Probably had something to do with the reflection. All right, so I did a little bit of research and actually learned something new in this process. If we're doing transmission or reflection where the incident angle is perfectly normal to the diffraction grating, then this is our equation, d sine theta, and this will be the diffracted angle, so we'll denote that as theta m for m is 1, 2, 3, etc., is equal to m lambda. This is true if our incoming ray is perfectly normal to the surface, and that's for transmission or reflection. But in a situation like this where we come in at some angle, right? This would still be the diffracted angle, but now we have some new incident angle. And the equation changes slightly, which again, I didn't know this in all my years of teaching until this experiment blew up. Oh, no. Sine of theta m equals m lambda. Okay, so I had to go back and look at the video from when we had the laser beam, and it looked kind of like, and this is a rough guess, that the laser beam was coming in at about a 30-degree angle. So I had to just look at the apparatus and see how is it set up. So if our incident ray was 30 degrees, I ended up doing a little bit of work in Excel and had it pre-calculate these things for me, knowing that our incident ray was 30 degrees, and using the same assumptions that we had before, right, where the CD was somewhere between 4 and 5, the DVD was somewhere between 1 and 2, and then the Blu-ray was, of course, 0, which wasn't very useful. I ended up coming up with some of the following ranges or calculations. So for the CD, solving this equation a little bit differently, we wanted to find D. So I said D was pretty much m lambda over the sine of 30, which I think is, how did I program that? 1, 2 over the square root of 3? Yeah, so that'll be 1 half, plus the sine of 90, the maximum possible diffraction angle we could get. I had Excel solve this equation and pretty much just spit out what were the D values for various M's. And in the case of the CD, D ranges between these two values. This is 1.42 to 1.77 micrometers. And the DVD ranges between, looks like 0.7 micrometers to 1.1 micrometers. And of course, the actual technical specifications are 1.6 and 0.74. So these do fall in between these two ranges at about here. So we did, in a way, kind of find, assuming we had the proper physics involved and had this correction in mind, we predicted, here are the possibilities for what that pitch, or not pitch, what the groove spacing could be, or the density of the lines in the pre-groove on the disc. The Blu-ray can't possibly be solved this way, not really well, because one of the M's was 0, right? We didn't have an extreme case. We didn't even have one to compare to, so it could be anywhere, right? It was completely unknown and unsolvable in a way. But I kind of rearranged the equation, said, okay, knowing what we saw, or rather knowing what the technical specifications are for these different things, right? 1.6, 0.74, and 0.32 micrometers. Well, let's rearrange the equation and figure out what's the maximum M that would correspond to sine theta m equals 1, where this is 90 degrees. Okay, and in doing that equation, it would look like, I guess if this was D times sine of the incident plus sine of the final equals m lambda. Rearranging that was as simple, or rather, D over lambda sine 30 plus, I guess, 1, because that was sine 90, that equals m. Sorry about that. So in these cases for the CD, I got m was equal to, looks like 4.511. The DVD was 2.08, and the Blu-ray was 0.9. So compare these two, what do you expect, right? We don't see a fractional m. We see it at the integer value. So that means we should see 4 spots above the center max, 2 spots above the center max, or 0 spots above the center max, meaning you only see the one in the center. And if we go back and look at our original data, what did we see? Here with the CD, we saw 4 out, and check the video again. Just rewind and take a look. DVD was at 2, and the Blu-ray, we saw nothing. And those seem to correspond pretty well to some of these things here that we predicted we would see. So it's just an interesting, just kind of an interesting, neat little trick to do with the CD. It is a diffraction grating, so just play around with it and you can see how it behaves.